Okay, we're going to finish the notes from yesterday. So finishing up where we left off at the end of class was number 5, where you were hopefully figuring out that we had a sphere formed by revolving the curve y equals square root of 36 minus x squared around the x-axis. So square root of 36 minus x squared gives me that blue semicircle, and then I revolve it and I end up with a perfect sphere. So of course geometry does work here. I can do the volume of a sphere by my formula 4/3 pi r cubed, and hopefully you determined that the radius was 6 based on my equation that I have over here. And doing the math here, we end up with 6 cubed is 216, so I end up with 4/3 times pi times 216, giving me a total of 288 pi units cubed for my volume of that sphere. Easiest way to do that problem by far. But, of course, we can do calculus for this, so we can use our same method of slicing this sphere into a whole bunch of circular discs, which are really very, very, very thin cylinders. And we find the area of one cylinder, multiply it by the width, the height of the cylinder, which is the width in this picture, dx. And that's what I've done over here. So I've got volume using my integral formula, integral from -6 to 6 as my limits, since I have determined that my radius is 6, of my radius squared. That's my radius, but when I square that, that ends up canceling out with the square root, and that's why I ended up with just having 36 minus x squared inside my integral, and I'm ready to integrate. Multiplying it by dx for my thickness. There's my dx, the thickness of my cylinder, one of my cylinders, or one of my slices, and then multiplying by pi. I did pull the pi out. So once I integrate, I'm ready to substitute in my 6 and my -6. So first, let's substitute a 6 in here for my x. So I'm going to end up with pi times 36 times 6 gives me a 216 minus 6 cubed over 3 is 72. And then I'm going to go ahead and substitute a -6 in for my x here and here. And I'm going to get a minus 36 times -6 is -216. And then -6 cubed divided by 3 gives me -72. I'm subtracting a -72, so it ends up with a positive 72. Simplifying that, 216 minus 72 is 144. I have a -144, but I'm subtracting a -144, which ends up with adding it. So I'm getting altogether 288 times pi, which is the exact same thing that we got over here for my volume. Okay, of course, the calculus way was longer, but I wanted you to see just a different example of where the geometry gives me the same answer as what my new method of integrating is getting me. Okay, time to move on and take a look at something a little bit more complex. As we do that, I'm going to take us back to where we started yesterday, which was with the volume of a cylinder. So find example 1, we're going to do a quick look at that, and then we're going to go to example 6, because example 6 is almost the same as this. The difference is that when we get to example 6, we're going to be taking my cylinder and we're going to be drilling a hole out of this cylinder is the best way I can describe this. So we're going to be hollowing it out, and the solid that we're going to be talking about is not actually a solid cylinder, but a cylinder with a hole in the middle. Picture taking this and literally drilling out a hole from the center and finding the volume of the remaining part. That's the preface for example 6. So go ahead and find example 6 and let's work through it. I'm going to make you redraw it. And notice this time we've got this extra information that we've got the line y equals 3 and the line y equals 2. That's what I was just referring to as I was talking about drilling out of the center. This line y equals 2. Still going from 1 to 5. And I've got the line +3 and -3. So So let's go ahead and sketch this cylinder in. So original cylinder looks something like this. And then I'm going to throw in the line y equals 2, and I'm going to use a different color here. Let's go ahead and use green for the inner circle. So I'm going to use, throw in the line y equals 2, and basically draw another cylinder inside my first one. As best as you can do that. I know it's hard to draw these, but I think it's important that we can picture what's going on here. So give it your best attempt. So what I'm going to do here is I'm going to, of course, start with the geometry. And geometry tells me that I can do this by simply finding the volume of the first cylinder, the blue cylinder, which is exactly what I did in example 1, and then subtracting the volume of the green cylinder, the inside, taking it away, so I'm left with the remaining volume or amount of solid that I have. So let's do that. Recall pi r squared times height is my volume formula. And all I'm going to do is I'm going to do that twice, recognizing that in the first one, my radius is going to be a 3. And then in the second one, my radius is going to be just 2. So this one is going to be a 2. So calculating, I've got, in both cases, my height is going to be 4. That's because I'm going from 1 to 5. So this actual length in my picture, but really the height of the cylinder is a 4. So we're going to end up with 36 pi. We already calculated that for example 1 yesterday. 36 pi for my volume of my blue cylinder minus the other one. 2 times 2 is 4 times 4, 16 pi, giving me a remaining volume once I take the inner cylinder out of 20 pi units cubed. Okay, so just what we did, found the volume of the inner cylinder, found the volume of the outer cylinder, subtracted the two. Okay, preface for today is that's what we're going to do. So let's look at how calculus can help us solve this problem, because you know what's coming is, what if it's not a cylinder? What if we have some kind of a curve, and then we rotate that, but we also have another curve here, and we rotate that around an axis? Okay, so that's what we're preparing for. Calculus tells me I can use an integral to calculate the area of something, sum up a whole bunch of them, so that I'm ending up with actually a volume. So let's see what I can do based on what we did yesterday. Let's take out a slice of this cylinder. So I'm going to take out one narrow slice. Yesterday referred to this as a disc. And today I'm going to say that it's going to look a little bit more like a washer, because what you're going to notice is that you've got that outside circle, but again we've got that inner circle. So when I take out one of these discs, it's actually going to look in 2 dimensions. If I'm looking at this flat now, there's going to be the outer circle, and then there's the inner circle. And I'm trying to find the area of, or express the area of, this region that's outside of the green but inside the blue. Okay, if I can express the area of one of those washers that I now have, a disc with a hole in the middle of it, then I can multiply it by dx, which is the thickness of that washer, really, really tiny, thin slice, multiply by dx, that gives me the volume of the washer, and I can add up a whole bunch of those volumes to get my volume of my entire solid that I've created. Okay, so let's express the area of this washer that I have as the area of the big circle. So I've reduced this to really a geometry problem, which is the area of the big circle minus the area of the small circle, which is the green circle. And if I can do that and find the area, I'm going to propose that I can multiply that by dx, which is my thickness, and then sum up all of my, oops, not from 1 to 4, sum up all of those volumes from 1 to 5. So in this case, we already established that my radius of my bigger circle is 3, so I'm going to have a 9 pi, and then I'm going to have minus radius of this is 2. So I'm going to have 4 pi, and I'm doing the integral from 1 to 5 of 9 pi minus 4 pi dx, and of course 9 pi minus 4 pi is 5 pi. I can pull all of that out, so I really have, because that's a constant, 5 pi times the integral from 1 to 5 of dx, which gives me 5 pi times x for my integral, my antiderivative of dx, x evaluated from 1 to 5, and x evaluated from 1 to 5 is really 5 minus 1, so I'm ending up with 5 pi times 4 and lo and behold I get 20 pi units cubed, exactly what we ended up with by doing our geometry. Okay, what I want you to focus on is this part right here, the setup of my integral, because I basically did pi times big radius squared minus pi times little radius squared, where I used blue and green to represent my two radii that I had. And we really could have pulled out the pi, so this could have looked like pi times integral of radius squared minus radius squared, all inside of my integral. That's going to look familiar. Okay, keep that in mind as we move on to example 7. I think we're ready for it. And you'll understand the point of why we did this. Find the volume of the solid formed by revolving the region bounded by the graphs of y equals radical x and y equals x squared around the x-axis. So we're going to start, of course, with the graph. Y equals radical x and y equals x squared. And we are going from x equals 1 to x equals 5. I don't think we need that. Ignore that. That's a typo. So we're going to go ahead and sketch a quick graph. Y equals x squared and y equals radical x. And I'm looking for where these intersect. If you're not sure where these graphs intersect, we could do a little bit of quick algebra here. So we've got y equals x squared and y equals radical x. I want to see when those are equal to each other. So I'm going to square both sides because I want to get rid of the square root. And I'm going to get x is equal to x to the 4th. And I'm going to get x to the 4th minus x is equal to 0, giving me x times the quantity x cubed minus 1 equal to 0. So x is equal to 0 and x is equal to 1 are my two solutions. So that's why I said we don't need the limits in this case. And that was a typo, because what I'm going to end up with is I'm going to end up with an intersection region that I'm going to then revolve. So let's go ahead and go from 1, I think this is all we're going to need, 1 to 1, or 0 to 1. And I'm going to do y equals radical x first. Something like this. And you can keep it going. And then y equals x squared for my other one. And I'm going to take that region that I've just created and I'm going to revolve that around the x-axis. It's going to look kind of weird, but this is what it's going to look like. So there's my radical x flipped over. Here's my x squared flipped over. Something like that. Got a little bit smaller in the process of flipping it, apparently. And what I'm going to do is I'm going to take that and picture making a solid. And here's where you're going to have to kind of have some visualization powers for 3 dimensions. It's going to look somewhat like a bowl, but then it's going to be kind of inverted on the inside. So geometry is going to fail me, obviously, in this case. I set you up for this one. We're going to go straight to the calculus. Let's try to look at a slice of this. And what's going to happen is I'm going to have that inner circle. So at the top, I actually don't have an inner circle, only at the very top, because my curves are intersecting there. But every other spot along there, the thickness is changing of how wide that washer is. But I'm going to end up with those 2 circles. And so what I'm going to do is I'm going to find the volume by doing pi times radius squared minus pi times radius squared, which is area of the big minus area of the small. So I'm going to get area of that washer, and then I'm going to multiply that times dx, which is the thickness of one of those washers. So I'm going to go ahead and pull the pi out because I know I'm able to do that. So I'm going to factor out, or I shouldn't say factor out, I'm going to pull the pi out since that's a constant. I'm going to note that I'm integrating from 0 to 1. And then I'm going to note that this first r is really my big radius. That would be the radius of the outer circle, which is created by my outer curve, which is radical x. So that's going to be radical x squared. Putting in my function, in this case it's the outer function, or the upper function, you could think of it that way. So that's my big radius squared, minus my little radius is my inner function. So that is, this inner circle is created by my lower function, which is x squared. And I'm squaring that because my formula is square it. And then I'm going to have all of that times dx. So what I have right here is representing actually the area of one of these washers. And then my dx is really representing the thickness of the washer or the height of the cylinder. I'm finding the volume of one of those, adding up a whole bunch of them to get the volume of the entire saw. Okay? We're ready to integrate, but I would probably simplify this first. We've got from 0 to 1. Radical x squared is really just x, and x squared squared is x to the 4th. So that's going to make it a little bit easier for my integration. I'm going to get pi times x squared over 2 minus x to the 5th over 5. Evaluating that from 0 to 1. And now we're just in calculus mode, and we're just doing the math. So I've got pi times, don't forget about that pi. I'm going to put big brackets, and I'm going to note that first I'm plugging in the 1 for a limit of integration. So plugging in the 1, I'm going to have 1 squared over 2 minus 1 to the 5th over 5, minus, plug in the 0. So I've got 0 squared over, and that ends up just being 0. We've seen that a few times. So I've got 1/2 minus 1/5, and I should be getting common denominators for that. 1/2 minus 1/5, 10 is going to be my common denominator, so that's going to be 5/10 minus 2/10, giving me 3/10 times pi, or 3 pi over 10 units cubed for my volume of the solid that we created by wrapping that curve around my x-axis. Okay, so that's a case where the geometry fails and we have to use our method. Conclusions, if you didn't catch it, conclusions are pretty much right up here with what I did, but let's go ahead and write it up nicely for ourselves. The volume of a solid can be created by taking pi times the integral of, yesterday we just had f of x squared dx, because my f of x was my radius. So the difference here is that I'm going to have two functions. I'm going to have an f of x squared for my outer radius, and then I'm going to have minus an f of x squared for my inner radius dx. And you're going to need to, sometimes they say use r, capital R, to note that that's my bigger radius, and lowercase r to note that that's my smaller radius. So it doesn't matter what you use as long as you know that this is my bigger radius, and then this is my smaller radius. Okay, so that gives you a formula, if you will, of finding the volume of any solid as long as we're integrating with respect to x, but I think you could probably figure it out how to change that for y. That's what you're going to try in the next problem.